Okay, welcome to today's lecture. Today's lecture is about chemical equilibrium. Objectives. First and foremost, I'm going to start by teaching you on the equilibrium constants. After that, we'll look at Kc and Kp relationships. After that, I'm going to teach you on the relationship between equilibrium constant and Gibbs energy. And lastly, I'm going to teach you on the factors affecting chemical equilibrium and also look at the Le Chatelier principle. So before I start, just ensure that you subscribe to this channel so that whatever I'm going to be posting, you'll be notified or updated. For today, we'll look at the equilibrium constants. So before I teach you on the equilibrium constants, you need to know or to understand what chemical equilibrium is. So what is chemical equilibrium? So chemical equilibrium is a state in which the rates of the forward and reverse reactions are equal and the concentrations of the reactants and products remain constant. So in a chemical equilibrium, the rates of the forward and reverse reactions are equal. So just by the word itself, equilibrium means equal. And the concentrations of the reactants and products remain constant, or in other words, they remain unchanged or same. So we need to understand what equilibrium is. So equilibrium is a dynamic process, meaning the conversions of the reactants to products and products to reactants are still going on, although there is no net change in the number of reactant and product molecules. So there is no net change in the number of reactant and product molecules despite the conversions of reactants to product and products to reactants going on. For example, you're having this reaction here. So this is nitrogen tetraoxide decreasing with time in order to form nitrogen dioxide like that. And then in between, you are seeing this symbol here. So this symbol means this reaction is reversible. So either side it's possible. And then we can have these two graphs that will help us understand what I'm from explaining there. So this first graph, we have concentration, expected concentration against time. You are seeing nitrogen tetraoxide decreasing with time in order to form nitrogen dioxide, which is increasing with time. And then here we are having rate, which is plotted against time. We are having the forward rate and the reverse rate. As you can see here, these two are meeting here, so meaning this reaction is at equilibrium. So as we said, chemical equilibrium, the rates of the forward and reverse reactions are equal. So here the concentration of reactants and products remain constant. They're just the same. Now that you know what chemical equilibrium is, let's look at the equilibrium constant. So what is equilibrium constant? Equilibrium constant is the ratio of the equilibrium concentrations of products over the equilibrium concentrations of reactants, each raised to the power of their stoichiometric coefficients. I will make you understand this. Just pay extra attention. So for you have the reaction of the type, you're having this reaction here. So A and B are reacting to form C and D, and this reaction is balanced. So A, B, C and D are representing the chemical species, while J, K, I and M are representing the stoichiometric coefficients. So as I was saying, where A, B, C and D represent chemical species, and J, K, I and M are their coefficients in a balanced equation. So this equation should be balanced. Ensure that any equations dealing with equilibrium should be balanced. In a balanced equation, the law of mass action is represented by the following equilibrium expression. So for example, you ask the question to say, write the equilibrium expressions for the reaction above. How can you write the equilibrium expression? So this K you are seeing, that's the equilibrium constant, is equal to, as we said just by the definition, equilibrium constant is the ratio of the equilibrium concentrations of products over the equilibrium concentration of reactants. So we'll start with the concentration of products here. So I'm going to write a square bracket, meaning the concentration of the product. So I'm going to write C, and then the products we have in C and D like that, over, since it's saying over the equilibrium concentration of reactants, So you're going to write the reactants here. So you're having your reactants A and what? B, like that. And then just by the definition, we said equilibrium constant is the ratio of the equilibrium concentrations of products over the equilibrium concentration of reactants, each raised to the power of their stoichiometric coefficients. So we need to know the stoichiometric coefficients of each these species we have written here, the concentrations here. So for C, we are having I, so we raise it to become the power, and then for D, M, that's the coefficient for D. Then for A, we are having J, like that, and then for B, you are having K, like that. So that's how you go about this. When you are taught to write the equilibrium expression, that's how you're supposed to do it. Just have to write the concentration of the products on top, and then over the concentration of the reactants down, and then each raised to their stoichiometric coefficients. Then you are done. So this is what I'm from illustrating here, as you can see. So this is what I'm from explaining, and I'm sure it's clear. So the square brackets indicate the concentrations of the chemical species at equilibrium, and K is a constant called the equilibrium constant, as I said. So I'm sure this is clear to you. Now let's look at the other part. Okay, now let's look at law of mass. You need to know what law of mass is. So law of mass action says the value of the equilibrium constant expression Kc is constant for a given reaction at equilibrium and at a constant temperature. So this Kc, the equilibrium constant expression, is constant for a given reaction at equilibrium and at a constant temperature. Again, the equilibrium concentrations of reactants and products may vary, but the value for Kc remains the same. So the value for Kc, which is the equilibrium constant, remains the same, remains unchanged. But for the equilibrium concentration of reactants and products may vary, may change. Again, we need to know about the magnitude of Kc, the magnitude of the equilibrium constant. So if the Kc, the equilibrium constant, if Kc value is large, meaning Kc is greater than 1. What does it mean when it's greater than 1? What does that mean when Kc is greater than 1? When equilibrium constant is greater than 1, what does that mean? So here, if the Kc value is large, meaning your equilibrium constant is greater than 1, what does that mean? The equilibrium lies to the right, and the reaction mixture contains most products. So that's what it means. So when your Kc is greater than 1, just know that the equilibrium lies to the right, and the reaction mixture contains most products. And then if the Kc value is small, what does that mean? When your equilibrium constant is less than 1, what does that mean? It means the equilibrium lies to the left, and the reaction mixture contains most reactants. It's containing most reactants when it's less than 1. And then if your Kc value is close to 1, meaning your equilibrium constant is in the range, or it's between 0.1 and 10, meaning the mixture contains appreciable amounts of both reactants and products. So now let's do some calculations, so that let me show you how to go about some questions, so that you can know how to answer questions, because we're interested in questions. So let's look at this important part now for questions, so that you can understand clearly. So now, writing equilibrium expressions. You need to know how to write the equilibrium expressions. So you're having this question. It's saying write the equilibrium expression for the following reaction. So you're having this ammonia plus water, and then showing this reaction is a reversible reaction. It's at equilibrium, forming nitrogen dioxide and water, like that. So the question is asking you to find the equilibrium expression for this reaction. So how can you write the equilibrium expression? So I'm sure you know. So this K, that's the equilibrium constant, is equal to, we're going to write the concentrations of the products for this. So we are having nitrogen dioxide, like that, and then we are having water, like that, and then over the equilibrium concentrations of the reactants, like that. Then you're going to have O2 like that, and then each must be raised to their coefficients. So nitrogen dioxide is having 4, and then water is having 6, and then ammonia is having 4, and then oxygen is having 7. So just by doing this, then you're done. So this is how you write the expression, the equilibrium expression. I'm sure it's clear. Now let's do the other question, the last question, so that you can understand clearly. So here now, calculating the values of what? K. So here I'm going to show how to find or how to calculate the values of K. So the question is saying the following equilibrium concentrations were observed for the upper process for synthesis of what? Ammonia at 127 degrees what? Celsius. So the concentration has been given for ammonia. We are having 3.1 times 10 to the power negative 2 mole per liter. And then for nitrogen concentration, we are having it to be 8.5 times 10 to the power negative 1 mole per liter. And then for hydrogen, we are having the concentration to be 3.1 times 10 to the power negative 3 mole per liter. And then the question is asking us to find, is asking us to calculate the value of K at 127 degrees Celsius for this what? Reaction. So first thing, let's come up with solutions. A. So what are you supposed to do here? You know that this is the upper process. Upper process is a process by which ammonia is manufactured. So you need to know what happens for ammonia to be manufactured. So what will happen here is nitrogen plus hydrogen will react in order to form NH3 like that. And then you need to balance this. This side you're having 3 hydrogen, this side 2. So what are you going to do? You can write 2 here, and then nitrogen has become 2, even this side it's 2. And then for hydrogen it's having 2, but this side is having 6, so we can write 3 in front of hydrogen like that. It's balanced because you need to come up with a balanced reaction. So here it's balanced now. So what's the second step now? Here we want the value of what? K. We need to solve K. So since we have come up with this reaction, we need to come up, we have come up with the equation, the reaction for the upper process for ammonia. Now let's write the equilibrium what? Expression for this. So how can you come up with the equilibrium expression for this? So you need to know that the product should be on top, the equilibrium concentration of the products on top like that, over the equilibrium concentrations of the reactants. So you are having N2 like that, and then this side you're having hydrogen like that, but each must be raised to their stoichiometric what? Coefficients. So for ammonia the coefficient is 2, and then for nitrogen same as 1, nothing there. So even if I haven't written anything on top, it's okay. And then for hydrogen it's having 3 like that. So after writing this, now you can substitute, because you're having the concentration for this, it has been given on top here, as you can see. So for ammonia it's having the concentration here on top, as you can see, it's 3.1. so we're going to substitute 3.1 times 10 to the power negative 2 mole per liter like that, raised to power 2. And then nitrogen is given to be 8.5 times 10 to the power negative 1 mole per liter like that, raised to power 1, or just like that. And then hydrogen's concentration is 3.1 times 10 to the power negative 3 mole per liter like that, raised to power 3 like that. So that's how you do it. And then when you work out all this, on your calculator, don't forget it's so you multiply this 3.1 times 10 to the power negative 3 mole per liter, you square it. After square it, you need to work out the calculation of this down. So 8.5 times 10 to the power negative 1, you're going to, before you multiply this 8.5 to the power negative 1, you need to cube this 3.1 times 10 to the power, it's raised to power 3. After doing all the calculations, you're going to have your K to be 3.8 times 10 to the power 4 like that. So without units, so K is without what? Units. So that's how you find the K, and I'm sure it's clear to you. So I'm going to keep this K I'm going to write it somewhere here because we'll be using it. If you can remember what I said about the law of mass of action, and then you can understand here. So I'm going to keep that, and then let's do the other question. Let's do the other question so that you can understand clearly. So number 2, what is number 2 saying? Or what is it asking us to find? What is question 2 asking us to find? So question 2, so I'm going to keep this part, I won't lab because we'll be using it. So I was just going to do B like this. So question 2, what is question 2 saying? So calculate the value of the equilibrium constant at 127 degrees Celsius for the reaction. Now this reaction you are seeing ammonia starting in front like that. So ammonia is decomposing in order to form nitrogen and hydrogen, and this reaction is reversible, is at equilibrium. So here you are having ammonia now, NH3 like that, plus like that, and then here there is 3 like that. And then if you can observe, what's the difference between these two reactions, the first one and the second one? So here this reaction is the reverse of the first one. Here on the first reaction we have nitrogen and hydrogen reacting to form ammonia, but this side you have ammonia decomposing to form nitrogen and hydrogen. So it's the reverse. Now we can come up with the equilibrium expression for this reaction. So we're going to have the equilibrium concentration of the products on top, and then we're going to have hydrogen like that over the equilibrium concentration of the reactants. So we're going to have NH3 like that. Then each raised to their coefficient. So ammonia will be raised to power 2, hydrogen will be raised to power 3. So have you seen this first expression we had and this first one? It's just the reverse. In other words, it's a reciprocal. This one is a reciprocal of the first one. So this key I'm going to raise it. We're trying to find the power n. We're going to, so how can you make this reaction to be like the first one? How can you make this reaction? We are comparing this expression, equilibrium expression, with the first one. How can you make this one to be like the first one? How can you make to be like the first one? So for you to make it like the first one, since this one is the reverse of the first one, or in other words a reciprocal, we're going to raise it to negative what? Power. Negative power. This negative power just means the reciprocal. Or we're going to flip this to make it like the first one. So therefore our K, when it's same as negative what? 1, like that, it's same as negative 1. And I'm sure you're clear on how you're coming up with this one. We're trying to make this expression to be like the first one, because this one is the opposite, or it's the reverse of the first one. So therefore our K will be like this. So what's our K? Our K we have, so it's 3.8 times 10 to the power 4 like that. Now we're going to raise it to negative 1, because this one is a reverse, or it's a reciprocal, or you can say just 1 over K. It's the same with this negative power like that. So once you work out this on your calculator, 3.8 times 10 to the power 4, you raise it to negative power, you're going to get your answer to be 2.6 times 10 to the power negative 5. Note that your K is not supposed to have the what? It's not supposed to have the units. Then you're done just like that. So your K is 2.6 times 10 to the power negative 5 like that. So that's how you go about this one, and I'm sure it's clear to you. Now let's work out the other question, the question 3. Let's work out question what? 3. So what is question 3 asking us to find? What is question 3 asking us to find? So for question 3, the question is saying calculate the value of the equilibrium constant at 127 degrees Celsius for the reaction given by the equation. So here, see, have you seen, we have been given an equation on this question 3. So you're having 1 over 2 N2 like that, plus 3 over 2 hydrogen like that, and this is the Lewis reaction like that, having ammonia like that. Now here you need to observe what's happening, what's the difference, what's the change, what is happening for this to be 1 over 2. So for it to be 1 over 2 like this, it means they multiplied half to the first equation. Have you seen this nitrogen? You're seeing when you multiply nitrogen, this nitrogen on the first reaction, nitrogen with 1 over 2, it's going to be 1 over 2 nitrogen like that. Then when you multiply half with 3, you're going to have 3 over 2 like that on the hydrogen part there. And then when you multiply and then here you are supposed to have like that, yes. And then you multiply half with 2, here 2 will disappear. That's the reason we're not having 2 here. So they multiply this, the first reaction, with half. So this half, that's 1 over 2 you're having there. So what are you supposed to do here? Here you need to write again the expression for this reaction, the equilibrium expression. So we're going to have ammonia be like that, and then you're going to have nitrogen like that. So it will be 1 over 2, that's the power, and then hydrogen will be less to be 3 over 2. So here now your Kn, we want to find the power of n there so that we know what you're going to use. Okay, so how can you make this to be like the first one? We need to compare this reaction with the first one. We need to compare this with the first one. How can this reaction look like the first one? So have you seen this expression? This expression, how can you make this expression to look like the first one? Or what was happening? So here, what's happening is this. Since they used 1 over 2, when we factorize 1 over 2 in this reaction, it's going to look like the first one. It's going to look like the first. So if 1 over 2 disappears, you're going to have 1 over 2 as the power there, because it will become the coefficient. Or in other words, when you factorize 1 over 2 in this reaction, let me do this, 1 over 2 outside. So when you factorize 1 over 2, you're going to have your so when you factorize 1 over 2 in this same reaction, the first one, you're going to have nitrogen like that, plus, and then your 3 will remain like that. You're going to have nitrogen like that, and then you're going to have your ammonia like that, and then your 2 will be here when you factorize 1 over 2. And then this 1 over 2, have you seen? It will become, so this one is the coefficient, it becomes the coefficient, and this coefficient should be raised to the power according to what we said. So the coefficient becomes the power. So that's the reason why I factorized 1 over 2 in this. I want to make it look like the first equation. So when you factorize 1 over 2, it's looking like the first one we had, the reaction we had at first on part A. So now this 1 over 2 will become the power, will be raised to the power. So it will be like that. So our Kn will be like this, will be raised to 1 over 2. So when it's like this, what's going to happen? So we are going to say, what's your K? Your K we found at first, it's 3.8 times 10 to the power 4. So we are going to say 3.8 times 10 to the power 4. You do that, and then you do to the power 2, like that. So when you work out that on your calculator, 3.8 times 10 to the power 4 to the power 1 over 2, or you square root that, you're going to get something like 1.9 times 10 to the power 2, like that. So that will be your answer for K, for the last part. Then you're done. So that's how you go about this one. Now you are having these questions in your tutorial sheet. So the first question is saying, suppose the reaction has the equilibrium concentration, equilibrium constant K 1.3 times 10 to the power 8. What does the magnitude of this constant tell you about the relative concentrations of products and reactants that will be present once equilibrium is reached? Is this reaction likely to be a good source of products, and I'm sure I talked about the magnitude. If it's greater than 1, if your equilibrium constant is greater than 1 or is less than 1, what does that mean? So you're going to answer this and then write the equilibrium expressions for the for each of the following gas phase reaction. So I'm sure you can't fail to write your equilibrium expressions for these reactions. And then question 3 is saying at a given temperature you are having K to be 1.3 times 10 to the power negative 2 for the reaction. This is ammonia again. Now here you're not supposed to find for K because K has been already been found for you. And then the question is saying calculate the values of K for each of the following reactions. So this one you just have to be comparing with the first one, the changes, what's happening. And I'm sure this one you have already done it. It's the one I'm from doing. And then this one, have you seen the reverse of that one? I'm from doing it. And then what's happening to this one? For it to be 2. And then on the first part it's 1, but here it's 2. So this one was doubled. So they multiplied to throw out this. So you're going to know what you're going to come up with that. And I'm waiting for your answers. You should submit. And then when you're having challenges, don't hesitate to contact me or to call me. So lastly, don't forget to subscribe, like, share and comment, and thank you for watching.